Hello. We are going to talk about spin-orbit coupling, and I'm going to give you a quick diagram and then jump over to some really cool slides I totally found online. I'm stealing these completely, but they really talk about, link everything back to the history of why we needed spin understanding for the wave function. Anyway, so spin-orbit coupling. So you have your, here's the nucleus. You have your electron, and I'm going to just represent it by an orbiting mass. Not the best example, but whatever. So the electron is orbiting. And so if it has an angular momentum going around the orbit, there's going to be charge moving, accelerating, is going to create a magnetic field coming this direction. Okay, this is like a magnetic induction. So anytime you have an oscillating or a moving current, that's going to create a magnetic field going opposite or perpendicular to the orientation or its rotation. So I'm going to draw it this way. So there is your J. Okay, so this is the angular momentum. Oops, sorry. I should say that is L. My bad. So this is the L quantum number. It's going to have a magnitude associated with, so the magnitude is equal to L times L plus 1. That is 1/2 h bar. So this is not, so L is not the magnitude of that. L is just designating that this is the angular momentum of the orbital, or of the electron orbiting around the nucleus. Even though it's not orbiting around the nucleus, it's a wave dispersed throughout, but it has an angular momentum, L. Then, if you zoom in, you're going to have an angular momentum of the charge itself, S. Okay, so S has, so there's its spin, angular momentum, and the spin angular momentum arises from the fact that you've got a charge. It's also oscillating, and so because it's moving, so it creates a magnetic field at, or a magnetic vector at the electron. Okay, so that's its intrinsic spin. Orbital spin, intrinsic spin. Okay, so we know, however, that, so in this particular case, you can have this spin and this angular momentum can couple together. Okay, so you can have, I'm going to just draw this in red. You can have this net m sub L and this m sub S. Those and those can combine. Okay, so now those vector components are going to be coupling together. So this would be, well, they're coupled. So if you're going to be, say, bouncing something up and down, and then you got, say, and I'm now going to bounce up and down, me doing this, and then my body doing this, and they're going to couple together. Bad example. Go team. Anyway, so we then have the total angular momentum. Here comes J, is equal to L plus S. All right, so that is for a high energy state. Oops, that should be lowercase j. You can also have L, and so the vectors here, so they would add together, and there's a great picture of this in the textbook, to where you've got L and then S. So then J would be that component, where it's L plus S. But then you could also have S. What happens if S is spin down? Then your L and your S and your J becomes, whoops, whatever. So there's J, there's S, and there's L. So it can be either L plus S or L minus S, and this is the lower energy state. So when they're coupled together, they have an increase in energy. So your angular momentum and your spin coupled together, you have an increase, higher energy state. If they are down, so one is going one way and the other one's going the other way, they're going to, much like spin up and spin down is a lower energy state. If they couple this way, then they're going to be a slightly lower energy state. So that would be, J would be L minus S. And so J would be slightly smaller. Okay. This is what drove Pauli crazy. This is known as, this can cause what's called the Zeeman effect. And this is how Pauli knew that there had to be some extra spin something. So I'm going to jump over to the data that showed this, but spin orbit coupling, orbital angular momentum, spin angular momentum, add together, subtract. Okay,